Welcome everyone. I would like to express our gratitude to Data Science Department that have Dr. Judy Ruiz is the program director and our capstone project instructor Dr. Mario Misekin, our project advisor Dr. Jiwat Sita, and project sponsor Dr. Faye Anderson. We are Team Triforce Analytica. We are Elisha, Henley, and Magnus, students in the Master Degree in Data Science program. Our logo is on the edge left corner. Our project title is Leveraging Machine Learning for Advanced Crime Prediction in Los Angeles. Today we are presenting the first two chapters of a total 5 main chapters. In our overview of the first two chapters, we examine the urgent need for proactive, data-driven policing in Los Angeles against rising crime rate. We discuss employing advanced analytics to identify crime hotspots, analyze victim demographic, and assess the weather impact on crime. Our approach suggests machine learning can predict crime using multiple data points. We outline the study limitation and explain key methodologies like LSTM, ONN, ARIMA. Our goal is to enhance public safety through improved crime prediction and strategic resource allocation. The literature review scrutinized over 40 references from 1990 to 2024, indicating a shift to AI and machine learning for crime prediction, emphasized the need to incorporate various data such as victim information and weather data condition to accurately predict crime. Our research is driven by clear objectives to advance predictive policing in Los Angeles. We aim to identify crime hotspots, understanding that crime is unevenly spread across the city, and analyze the role of victim demographic in crime patterns. Furthermore, we explore how weather conditions influence crime frequencies, constructing a model that integrates meteorological data with crime records. These objectives are pivotal for deploying police resources effectively and enabling target crime prevention strategy. By achieving this goal, we anticipate providing the LAPD with a multifaceted predictive tools that not only forecast crime occurrences but also offer strategy insight for primitive action through the advanced analytic and machine learning. Next, I pass to my team, Elisha. Continue.
So for section 1.4, which is our research hypothesis, we're seeing that other studies are showing correlations to weather and victim demographics when it comes to crime prediction. A recent study by Sabak Tarashvili saw a decrease in error when including weather data into a crime prediction model in the city of Little Rock between 2017 and 2023. Additionally, in another study from 2015 to 2018 in Southeast China, Zhang discovered patterns in victim demographics that intersect with criminal occurrences as well using machine learning algorithms. Last, LSTMs and RNNs appear to be effective choices for spatiotemporal crime predictions for hotspots, supported by several studies like Yuki, who achieved an accuracy of over 99% of preemptive crime location prediction in Chicago 2019. During the Chapter 2 section of this presentation, we will discuss several more studies that support our research. Overall, there appears to be a lot of success in supporting research to our original research hypothesis of weather and victim demographic predictions in LA crime, as well as predicting crime hotspots. Moving on to section 1.5 of chapter 1, study limitations. Our research still faces several possible limitations, more of which have been revealed while performing our research. Our original limitations include lack of perpetrator demographics, bias in model transparency, geographic limitations, and short time frames. So we've hopefully alleviated the time frame issue by incorporating historic data from 2010 to 2019 to better help with our forecasting models and allow our other models more access to training data, as well as address issues like seasonality or crime changes during the lockdown years of COVID. Some new limitations include the weather stability in Los Angeles, as it historically only rains for a small part of the year. Due to data nonlinearity, complex models may be more necessary than before, and multiple models may need to be created as suggested by Kim in 2023 to provide a more robust analysis. This creates bigger issues with model transparency and hyperparameter tuning. Some studies, such as a study by Bell in 2022, suggest that model transparency may be more nuanced, and selecting more complex models may not necessarily be less transparent than others in some cases, which is hopefully true and can help ease our model transparency problem.
Hello, everyone, and thank you, Elijah. Our definition of terms section is by no means exhaustive. However, the following are some of the terms we have defined in our paper. From RNN, recurrent neural network, which is a type of artificial neural network that uses sequential data or time series data, to long short-term memory, LSTM, which is a special type of RNN that addresses the vanishing gradient problems of RNNs, to ARIMA, autoregressive integrated moving average, which is a statistical analysis model that uses time series data to understand a data set or to predict future trends. We have others like gradient boosting machines, decision tree, we have random forest, support vector machines, and so on. Spatiotemporal data analysis is one of such terms in our definition of terms. This is an example of a spatiotemporal data analysis, an analysis of data collected across both space and time. Spatiotemporal crime hotspots will uncover patterns of crime across geographic locations over a certain period of time. We see the spatial clustering of drug-related crime in Chicago from 2016 to 2019 in a 2021 paper by Xia Zhiyue and his colleagues in this slide. In our literature review, we delve into crime prediction, the transition from traditional statistical methodologies to advanced machine learning and AI techniques as a pivotal paradigm shift in predictive policing. Hernandez, 1990, in his paper, described this evolution technological progress in law enforcement practices. Yinglong, Yuki, Sarada, Hadain, Khan, Wu, and Zhang, amongst others, in their papers, highlighted that crime is influenced by several factors, including socioeconomic conditions, demographics, access to resources, law enforcement presence, community dynamics, and environmental factors. Now I'll hand it over to Hengli on crime prediction fundamentals.
For this slide, there are two main sections that pass our literature review. First, fundamental of crime prediction. Studies have progressively refined crime prediction by integrating geographic data, AI, and machine learning. Yinglong 2018 enhanced model with Google Places data, while Sarada and Sharma 2021 focus on crime type and AI for law enforcement strategy. Ross Hengar 23 highlighted the importance of spatial temporal factor in forecasting crime. Second section is challenge in combating crime. From 2020 to 2023, highlighted challenges in crime prediction, emphasized sociology, economic bias, data complexity, and ethical concern. Yale 2020 noted how bias affected model accuracy. Sama 2021 discussed the need for precision post-UCR, while Wu 2022 tackled data bias and inclusion of children mobility. In 2023, Raji focused on crime influence and false positive in machine learning, and Sabakari Vili addressed the struggle in resource allocation and tradition method in high crime area. Thank you.
Referring back to the study in Little Rock by Sabaktarishvili in 2023, weather conditions derived from the Little Rock Airport Adams Field were able to help capture dynamic relationships between weather and crime trends. Our study will implement a similar tactic by utilizing weather data from the LA Airport Weather Station. Utilizing various aspects of weather data, Yao in 2022 and Solomon also in 2022 saw improvements in accuracy when incorporating weather data when predicting crime. During the methodology section coming up, we plan to see improvements in our models as well as for Los Angeles. But on the topic of algorithms, a common theme used by several researchers is the deployment of several models for accuracy comparison, and even using multiple models to complement each other. For example, Sharma and Sarada both utilize several algorithms such as decision trees and random forests and LSTM models. Other researchers like Kim in 2019 and Bob Cura in 2021 utilized KNN and naive bias. In a strong majority of the papers, sometimes a dozen models or more are compared. So for our thesis on LAPD crime prediction using machine learning, we plan to take a systematic approach in testing and implementing the most appropriate algorithms in a similar manner as these researchers, as well as gathering more historic weather data to complement the addition of the 2010 to 2019 data set. So I want to briefly talk about the graphic on this slide, which is a web of related works when it comes to crime analysis through machine learning. Every time you click on a different paper, it creates a new web showing you related works. So we can see at a glance just how much recent research has been done in this field. So to conclude our Chapter 1 and Chapter 2 update, there's an abundance of research employing several different models and using several different types of data to refine the topic of crime prediction. Most of the studies we researched have implemented some algorithm similar to what we plan to do, or try to achieve a very similar objective with similar data in a different city or country. As long as we proceed with our study with a careful awareness of our limitations, and especially being careful to watch for bias, we suspect that our research hypotheses will still hold strong. So as we move on to Chapter 3, methodology, we will begin manipulating data through the rest of the data science and CRISP-GM lifecycle. This is our update for Chapter 1 and Chapter 2. Thank you.